Hello dear students. In the previous video we were discussing about the factors which are responsible for stabilizing the nucleus. So we already discussed the neutron to proton ratio. So according to this neutron to proton ratio, for the stability of the nucleus, the n by p ratio, so that is here the n by p ratio should be less than 1.56. So then only the nucleus is said to be stable. So next let us discuss about the one more factor, so which is responsible for the stability of the nucleus is the mass defect. So the mass defect, so it can be defined as the difference between the masses of electrons, protons and the neutrons present in an isotope, and its actual mass is called as the mass defect. So the mass defect, so that is represented by delta m for an isotope, so can be calculated by using this relation. So that is delta m is equal to ZME plus ZMP plus A minus Z into Mn. So where Z is the atomic number, A is the mass number and M is the actual mass of an isotope. So for example, let us consider the helium atom. So the helium atom having the mass number 4 and the atomic number 2. So is composed of the two electrons and 2 protons and 2 neutrons. So these individual particles have the masses. So the mass of the electron, that is 0.0005486 AMU atomic mass units, and mass of the proton is 1.0072 AMU, and the mass of the neutron is 1.0086 AMU. And the mass of the helium atom is therefore can be calculated as the 2 into the mass of the electron plus 2 into the mass of the proton plus 2 into the mass of the neutron. So that comes out to be 4.032 AMU. So the actual mass of the helium as measured with the mass spectrometer is found to be 4.0026 AMU. So therefore the mass defect is calculated. So by subtracting the calculated mass of helium atom with the actual mass of the helium atom. So that is the calculated mass of the helium atom. So here we have calculated the mass of the helium atom, so that is 4.032, and the actual mass of the helium atom, which is determined by the mass spectrometer, is 4.0026. So the difference between the calculated mass of helium atom and the actual mass of the helium atom is found to be 0.03037 AMU. Okay. So next let us move on to the third factor, so which is responsible for the stability of the nucleus is the binding energy. So the binding energy of the nucleus is the energy needed to break a nucleus into its individual protons and neutrons. Or in other words, so the binding energy can be defined as the energy needed to decompose the nucleus, or the energy released when a nucleus is formed. So it is called as the binding energy. So that means the binding energy. So we know that the nucleus is composed of the protons and the neutrons. So the energy which is required to break the nucleus into its constituent particles, that is into the protons and neutrons, so we call it as the binding energy. Or so when the nucleus is formed by the protons and neutrons, so the energy which is released, so it can be also called as the binding energy. So, so how this binding energy is related to the stability of the nucleus? So we know that the binding energy is the amount of energy that is released when a nucleus is formed by the combination of the protons and the neutrons, or the energy which is required to break the nucleus into its constituent particle. So higher the energy which is needed to break the nucleus, so that is higher the binding energy, so more stable is the nucleus. So that means the stability of the nucleus will be high when the binding energy is high. So that means the protons and neutrons are bind very strongly. So therefore the higher binding energy is required to break the nucleus. So higher the binding energy and more the stable is the nucleus. So to compare the stability of different nuclei, so we can plot the nuclear binding energy per nucleon, or the average binding energy on the y-axis. So and the mass number on the x-axis. So as you can see, the stabilities of the different nuclei, so that can be compared by plotting the average binding energy and the mass number. So the curve, so that rises steeply. So initially, so the curve, the plot of mass number versus the average binding energy, so that will steeply rises initially, but gradually it flattens and it slopes down for the, especially for the nuclei of the large mass numbers. Okay, so from this graph, so we can draw some of the important features. Okay, so under that, the first one, the nuclei with the mass number 4, 12 and 16 have the high binding energies. So that means the elements or the nuclei having the mass number 4, 12 or 16 possess more stability. So that means they are quite stable. Okay. So the next factor which can be drawn is that the nuclei with mass numbers in the range of 40 to 90 have the highest binding energy. Okay, highest binding energy. So we can observe here, so up to here, so the average binding energy is high. So after that, the curve slopes down for the higher, large mass number elements. Okay, so the binding energy will be maximum for the nuclei having the mass numbers, so between 40 to 90. Okay, so those nuclei are said to be more stable. So for example, for iron, cobalt and nickel, the region of in the periodic table, so they have the highest binding energy. So the nuclei with the mass numbers greater than 100, possess lower binding energy. So as you can see, the average binding energy curve slopes down. So after the mass number 90, so the average binding energy slopes down. So this indicates that for the nuclei having the mass number greater than 100 will possess lower binding energy. So around the mass number 210, so here around the mass number 210, so the value is so low. Okay, so if you continue this plot for the temperature at 210 degrees Celsius here, so the curve, the average binding energy will be low, that the nuclei become unstable and that nuclei will exhibit the property of radioactivity. Okay, so the element which is having the higher mass numbers will have lower binding energy. So lower binding energy means the nucleus is said to be unstable. So the elements having the higher mass numbers will possess lower binding energy and they will exhibit the property of radioactivity. Okay, so the radioactivity will be exhibited by the elements having the mass number greater than 210. Okay, so this concept of binding energy is used to calculate the energy which is liberated during the nuclear reaction. So let's move on to the one more topic. So that is the group displacement. So this group displacement law, so it is important for the examination point of view. So according to this group displacement law, so here you can see when a alpha particle, so that is the helium nuclei, is emitted, so the new element which is obtained will be having mass number, okay, so less by 4 units, and the atomic number so is less by 2 units. Okay, so whenever an element emits an alpha particle, so the newly formed element will have mass number less by 4 units and the atomic number by 2 units. So the newly formed element will occupy the position 2 elements to the left in the periodic table than that of the original element. So for example, let us consider the disintegration of the uranium. So the uranium nuclei, so having the mass number 238 and the atomic number 92. So when it undergoes disintegration, so it emits an alpha particle, so that is helium nuclei, so that is 4 and 2. So this is alpha particle, So the uranium, when it disintegrates by eliminate, that is emitting an helium alpha particle, so according to the group displacement law, so the newly formed element will be having mass number decreased by 4 units, so that is 238 minus 4, that is 234, and the atomic number by 2 units. So therefore when the atomic number decreases by 2 units, so that means 90. So the element with atomic number 90 and mass number 234 is the thorium. Okay, so thorium will going to occupy the position 2 columns to the left in the periodic table than the uranium. Okay, so therefore according to the group displacement law, when a alpha particle is emitted, the newly obtained element will be having mass number less by 4 units and atomic number by 2 units. So and that element will occupy the position 2 columns to the left in the periodic table than that in the original element. So similarly, when a beta particle is emitted, so by a nuclei, so the new element formed will have the same mass number. So when a beta particle is emitted, so the newly formed element will have the same mass number, but the atomic number increased by 1 unit. Okay, so therefore, so when the atomic number increases by 1 unit, so it occupies a position 1 column to the right in the periodic table than that of the original element. So let us consider an example. So let us consider the example of the thorium. Okay, so thorium having the mass number 234 and the atomic number 90. So when this thorium emits a beta particle, so that means the atomic number is decreased by 1 unit, but the mass number remains same. So the emission of beta particle to occur, so a neutron must have changed to a proton and an electron. Okay, so that is a neutron should change into proton and electron. So this is beta particle. So thus during the beta particle emission, the number of protons in the nucleus or the atomic number of the element increases by 1 unit. Okay, so therefore when a beta particle emitted, so we know that the mass number remains the same. So therefore 234, the mass number remains the same, but the atomic number increases by 1 unit, that is 90 becomes 91. So the element having the atomic number 91, okay, so the newly formed element, so that is protactinium, so having the mass number 234 and the atomic number 91. So therefore when a beta particle is emitted, so the mass number remains the same and the atomic number increases by 1 unit. So already we have discussed about the binding energy. So that is, it is the energy released when a nucleus is formed from the protons and neutrons. Okay, so the formation of the nucleus from protons and neutrons is accompanied by the mass defect. So that is loss of defect. Already we had explained with the example. So in order to account for this deviation, so the scientist Austin, he introduced the term called as the packing fraction. So that packing fraction can be defined by the expression, so that is the isotopic weight minus the mass number divided by mass number into 10 power 4. So for example, the packing fraction for hydrogen isotope, so having the mass number 1 and atomic number 1 with atomic weight 1.0078. So the packing fraction can be calculated as the isotopic weight, so that is 1.0078 minus the mass number of hydrogen is 1 and the mass number is here 1, so into 10 power 4, so that is plus 78. So similarly, so if we calculate the packing fraction of chlorine isotope, so having the mass number 35 and atomic number 17, so with the atomic weight of 34.98. So if we calculate the packing fraction, so it will be minus 5.7. So in these examples, so we have observed that the packing fraction for hydrogen isotope is plus 78 and the packing fraction for chlorine atom is that is minus 5.7. So what is the conclusion that can be drawn from these two values? Means greater the negative value of packing fraction, greater will be the loss of mass, its nucleons, and hence greater will be the binding energy. So that is greater the negative value of the packing fraction, greater will be the stability. So therefore, the result in the greater stability of the isotope. Okay. So on the other hand, the isotopes having the positive packing fraction, for example, for uranium, thorium, radioactive elements, so will indicate the instability of their nucleus. So here, greater the negative value, greater will be the stability. Okay, so the positive values of the packing fraction indicates the instability of the nucleus. So the nuclei which is unstable, having the instability, so they will show the radioactivity. So the quantity of mass converted into energy varies with the manner in which the protons and neutrons are packed in the nucleus. So hence the name was given the packing fraction. Okay. So when you draw the graph between the mass number and the packing fraction for different isotopes, so here you can observe all the isotopes, so that is except the helium, carbon and oxygen they all fall on the smooth curve. So the low values of packing fraction for the helium, carbon and oxygen here, so they indicate their exceptional nuclear stability. Okay, so these elements, so that is the helium, carbon and oxygen will possess the exceptional nuclear stability. So the minimum value of packing fraction is near the atomic mass number of iron. Okay, so that indicates that the low value of the mass, that is the minimum value of packing fraction is near the atomic mass of the iron and the nickel. Okay, iron and the nickel. So these two atoms have the maximum stability. Okay, so the minimum value of fraction. So the nuclei with the mass number greater than 200. Okay, so they will have the positive value of packing fraction. So we already know that the nuclei with the positive packing fraction possess instability. So in addition to that, so you can also say that the nuclei with the mass number greater than 200, so that means they will possess the positive value of packing fraction, shows the greater instability. Okay, so it may be also noted that for a system is inversely proportional to its energy. So thus the nuclei with the negative packing fraction should be unstable, but it is not always in case of, because other factors also responsible for the stability of the nucleus.